I'd like to talk with you about the different types of seismic waves and how they can be used to locate the epicenter of an earthquake, and then later how we can measure the magnitude. So the three things we want to talk about are the types of seismic waves, locating an earthquake, the location where it occurred, the epicenter, and then determining the magnitude of the earthquake. So let's start here. Okay, there are two basic types of seismic waves, and those are surface waves, which are the red ones here, which run parallel to the surface of the Earth, and body waves, which run perpendicular through the interior of the Earth. The surface waves are the ones that cause damage, and these can only be felt if you're close to the location where the earthquake occurred. They tend to dissipate out rapidly as you move away from the earthquake. So if you're quite a distance away, you're not going to feel the earthquake. And those are the surface waves. The body waves cannot be felt. So even if you're near it, you're not going to feel these, but they can travel very large distances. And in fact, the body waves can travel through the interior of the Earth and uh, can be measured or at least detected on the other side of the Earth. And now we're going to talk about the different types of both surface waves and body waves. Over on the right here, we have the two types of surface waves. Those are love waves and Rayleigh waves, often referred to as L waves or R waves. Both of these, when they pass through an area, there is physical displacement of the material. You can see how these blocks are moving or squishing or coming together. And this represents a physical movement of the material. The love waves go side to side. And you can sort of see this undulating side to side. The Rayleigh waves go up and down. And if you were near the location where the earthquake occurred, you're going to experience both of these, and it's going to go side to side and up and down. It's going to cause things to get knocked to the left or the right, but it's also going to push things up and push things down. This is what causes all the destruction in earthquakes. Over on the left-hand side here are the body waves. The body waves, again, they do not cause damage, but they can travel very long distances. And we have two types. We have the P waves, which are pressure waves. And those don't have displacement as much as just pressure along the direction of the earthquake. S waves do show some displacement. This is a shear wave, and they do go up and down. They cannot travel through liquid. They can travel through solids. P waves can travel through anything. And a good way to think about this is think about in a bathtub, or I should say, if you have a spring or holding onto a spring and I tell you to create a wave, chances are you're going to move your hand up and down or side to side. And you're going to see the wave transmitting along that spring. That's an S wave. It doesn't matter whether you're going up or down or side to side for the body wave. But those are the S waves. Those are shear waves. For a P wave, imagine yourself in a bathtub, and I tell you to create a wave in a bathtub. You're going to push yourself forward. That's a pressure wave. You know inherently that you can't create a wave in a bathtub going side to side or up and down. Those are S waves, and those don't transmit through water. But by pushing it, you can create a wave. And those are the P waves. And those can go through solids, they can go through liquids, those can go through anything. Again, the S waves cannot go through liquids. They can go through solids, though. When we look at the body waves, the P waves are the fastest waves. We can think of those as pressure or primary, and they travel at about 6 kilometers per second, in this case in granite. And it does depend on the density of material. The denser a rock is, the faster the velocity will be. So if this were basalt, this would be greater than 6. If this were sandstone, this would be less than 6. But for granite, it's 6 kilometers per second. For an S wave, think of it as shear or secondary, the velocity is slower. It's 3.5 kilometers per second in granite. And over here, we can see distance on the horizontal axis, the arrival time, when it's going to arrive at a specific location, is on the left or the vertical axis. Let's suppose you're 2,000 kilometers away. then at 4 minutes from the initiation or the occurrence of the earthquake, you're first going to see the P wave because that is going to be the fastest wave. And then at some interval later, the S wave will arrive. Note here that the further you are away from the epicenter, the time arrival between the arrival of the P wave and the S wave increases. And that can be used to help us locate the earthquake. If the P wave and the S wave are arriving very close to each other, chances are you're very close to where the earthquake occurred. However, if the time interval between the P and the S wave is very great, then you're probably a much further distance away from where the earthquake occurred. This is a typical readout from a seismogram, or that it is a seismogram from a seismometer, and you can see the occurrence of these waves. This is prior to the earthquake. This is the first occurrence of the earthquake, and that's going to be your P wave, because that's the fastest of the waves. It may go up, it may go down, it doesn't matter, but the very first motion, and you would look right there where it departs from the horizontal. That would be the arrival of the P wave right there. And then you'll see we get a few more vibrations, and then we get the arrival of the S wave. And again, it's that departure from the norm. But the S wave is slower, so that's going to be the second wave to arrive. And then you get this big jumble of material here. Those are the surface waves. You will not see any of the surface waves if you're too far from the epicenter of the earthquake. So this may or may not be in the reading. But anywhere, you should be able to pick up the P wave and the S wave. The P wave, definitely. If there is a liquid in between you and the earthquake, such as the outer core of the earth, then not even the S wave is going to show up, and you'll only see the P wave in there. But in general, if you see all three, the first is going to be the P wave, the second is going to be the S wave, and then the surface waves, if they're there, are going to be the last arrival coming. This shows three different seismograms here, and in each of these you can see the arrival of the P wave. The second one to hit is the arrival of the S waves, and then this big jumble is the surface waves. And what we're going to show you now is how we can employ this to get the location of an earthquake. Let's suppose that here we are in DC, and you have a seismometer set up in your backyard, and you're recording to see if any earthquakes are occurring. So let's use this one for an example. And let's suppose that this is the reading you got. I'm going to change a few things here. Instead of Northridge, it's going to be Washington, D.C. Instead of time in seconds, I've changed that to minutes. And then we're going to look at our P and S wave. We'll assume that the P wave arrived at, right here, 4.4 minutes. And the S wave arrived here at about 7.8 minutes. And I read that directly off of here. And so the time interval between this is 3.4 minutes. And that's the difference in the arrival times between the P and the S waves. That's going to be what we're going to be using to determine how far away the earthquake was from us. Now, if I use this, you'll see I can measure 3.4, which is the difference in the arrival times between the P and the S waves, find that on my graph, and it represents that distance right there. Now I have to find a location on this graph between the P and the S wave where the time difference on a vertical line is 3.4 minutes. So I take this distance and I move it up and down here to see where it fits the best. And I see there is approximately where I have 3.4 minutes between the arrival of the P wave and the S wave. And it has to be on a vertical line. And then I project that vertically down, and I see on my horizontal axis that tells me that the earthquake occurred 2,200 kilometers from DC, where my seismometer was. Now I can go back to my map. I have a scale down here, and I can calculate 2,200 kilometers. There it is right there. And I can draw a radius around the DC showing 2,200 kilometers away. I know that the epicenter of the earthquake has to be somewhere on that circle, but that doesn't tell me specifically where on the circle. In order to that, I have to have three more readings. And let's suppose I have one in Billings, Montana, and another one in Houston, Texas. If I do the exact same thing as I did for the readings from DC with the readings from Houston and Billings, then I will see that they're only going to intersect in one point, That is called triangulation, and that's going to be the location of my earthquake. And that's how you're going to locate it. Any errors that you make in measuring the time difference or in finding on the curve is going to mean that these probably aren't going to be perfect, and your circles may not intersect at a specific point. But if you're very careful, they should. Now let's go on to magnitude. The magnitude of the earthquake is different, and we have three different methods to determine the magnitude. The first is the modified Mercalli magnitude scale. The second is the Richter scale, and the third is the moment magnitude scale. The first, the modified Mercalli scale, is a scale from 1 to 12. It's completely based on observations. And so with 1 being the smallest, not felt at all, up to 12, where the damage is nearly total. But all of these are based on what is felt by a person, whether furniture is moving, is plaster cracking, is masonry cracking, are buildings falling. But you can determine the magnitude of this earthquake by something that you felt. There are some advantages and disadvantages of this. The advantages to this one are that it is easy and simple to understand. It's the easiest one for me to explain to you guys. It's good for historical earthquakes. If we have a recording or a written account of an earthquake from the Romans or Greek times, we can go back and use this and determine approximately how big that earthquake must have been. The disadvantages to this, and there are numerous, is that it is very subjective. You have some people that will feel it was major shaking, other people think it's minor shaking. And it can be dependent on factors other than the earthquake strength. How strong are the buildings? Some poor countries, a minor earthquake will cause buildings to collapse, but in more westernized countries or in wealthier countries, they may be able to afford to build stronger buildings, and even a stronger earthquake isn't going to cause them to collapse. Another disadvantage, which I didn't put here, is that it does require people to be present. If an earthquake occurs in the bottom of the ocean, you're not going to be able to use this scale for it. So like I said, there are some advantages and disadvantages to all of these scales. The second one is the Richter scale, created by Charles Richter. And this one is based on the readings from a seismometer, specifically from the seismogram that we talked about before. And it deals with two things: the distance away, which you can determine from the arrival times of the P wave and the S wave. So we've already determined how we can do that. The other thing that has to be measured is the amplitude. And the amplitude is from the baseline. So here's the horizontal, and it's the departure from there. The largest wave, wherever it is, whether it's the P wave, the S wave, or the surface waves, measure the largest wave from this baseline up or baseline down in millimeters. And if we get that, we can plot here our distance, which we determined from the P wave and the S wave arrival times. And then we get the amplitude in millimeters from the departure from the mean. And once you plot those, you connect them, and where they cross this center graph, that will give you the magnitude. And the advantages to this one, well, one thing I wanted to go through first is that this is a exponential scale, that it is not a linear scale. A magnitude 2 is not twice as big as magnitude 1. It's in fact at least 10 to 20 times as big. And every time you go up one magnitude on the Richter scale, you can basically multiply that by a factor of 10. So compared to a magnitude 2, a magnitude 3 would be 10 times as large. A magnitude 4 would be 100 times as large as a 2. A magnitude 5 is 1,000 times as large as a magnitude 2. And that we can see in the scale here. You'll see the scale only goes up to 6. Major earthquakes start at 7. And the problem with that is that by the time you get to a large earthquake, sometimes you can peg these meters, but also small variations in here are going to be big differences in the magnitude. And for that reason, the Richter scale is really not good for large earthquakes, which is too bad because those are the earthquakes that we're really interested in. Another disadvantage is that it does require equipment. You have to have a seismometer and a reading in order to do it, unlike the Mercalli scale, which just is based on observations. But the advantages to this one is that it is objective. Every person should come up with the same magnitude based on their seismogram. And it is quantitative, so we can actually look at data and go back to it. But let's take care of this disadvantage. the fact that it isn't good for large earthquakes, which again, those are the ones that we are most interested in. And our scale basically does not work for those. So what do we do in the case of a big earthquake? We use the moment magnitude. The moment magnitude means that you actually have to go to the site where the earthquake occurred. You have to measure the length of the rupture along the horizontal distance. How long of a crack in the earth is it? How much movement was there along the rupture? Physically, did it move a foot or did it move 60 feet? And what's the strength of the rock around it? Is it a very strong rock, which would obviously create a greater force to break? Or is it a relatively weak rock, which will break relatively easily? Once you get all those measurements, then you can determine how much energy was released in the earthquake. And using the same scale we looked at before, knowing the amount of energy, then we can peg it at exactly where it is on the Richter scale. It's sort of the opposite. With the Richter scale, we determine the magnitude, and then we can estimate the energy released. With the moment magnitude, we calculate the energy released, and then we work back to the Richter magnitude in there. The advantage for using the moment magnitude scale is that it is great for large earthquakes. The disadvantage for this one, and there is a big one, is that it's expensive and dangerous. If a large earthquake has occurred in a region, we have to send representatives out there to go make these measurements. They're going to be going into an area where there's a lot of damage, there's a lot of death, there's a lot of destruction. It's not going to be easy, it's going to be dangerous, it could be filled with disease. There's going to be resources that are limited. And so this is going to, one, it's going to put that person in danger, but it's also going to require a lot of money to get them around. And so we reserve this method only for the largest ones where it has to be done. We are not going to use this method for a smaller earthquake where the Richter scale works just fine. So those are the basic types of waves and how to determine the location using triangulation and the various methods of magnitude. Thank you very much.